let's imagine we have a huge cloud of hydrogen atoms floating in space. When I say huge cloud, huge both in distance and in mass. If you were to combine all of the hydrogen atoms, it would just be this really, really massive thing. So you have this huge cloud. Well, we know that gravity would make the atoms actually attracted to each other. We normally don't think about the gravity of atoms, but it would slowly affect these atoms, and they would slowly draw close to each other. It would slowly condense. They'd slowly move towards the center of mass of all of the atoms. They'd slowly move in. And so if we fast forward, this cloud's going to get denser and denser. It's going to get denser and denser. And the hydrogen atoms are going to start bumping into each other and rubbing up against each other and interacting with each other. And so it's going to get denser and denser and denser. And remember, it was a huge mass of hydrogen atoms. So the temperature is going up. The temperature is going up. And they'll keep condensing. They'll just keep condensing and condensing until something really interesting happens. So let's imagine that they've gotten really dense here in the center. They've gotten really dense here in the center. And there's a bunch of hydrogen atoms all over. It's really dense. I could never draw the actual number of atoms here. This is really give you an idea. There's a huge amount of inward pressure from gravity, from everything that wants to get to that center of mass of our entire cloud. The temperature here is approaching 10 million Kelvin. And at that point, something neat happens. And to kind of realize the neat thing that's happening, let's remember what a hydrogen atom looks like. A hydrogen, and even more, I'm just going to focus on the hydrogen nucleus. So the hydrogen nucleus is a proton. If you want to think about a hydrogen atom, it also has an electron orbiting around or floating around. And let's draw another hydrogen atom over here. And obviously, this distance isn't to scale. This distance is also not to scale. Atoms are actually, the nucleuses of atoms are actually much, 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 much smaller than the actual radius of an atom. And so is the electron. But anyway, this just gives you an idea. So we know from the Coulomb forces, from electromagnetic forces, that these two positively charged nucleuses will not want to get anywhere near each other. But we do know from what we learned about the four forces that if they did get close enough to each other, that if somehow they're under huge temperatures and huge pressures, you were able to get these two protons close enough to each other, then all of a sudden the strong force will overtake. It's much stronger than the Coulomb force, and that these two hydrogens will actually, these nucleuses would actually fuse, or is it nuclei? Well, anyway, they would actually fuse together. And so that is what actually happens once this gets hot and dense enough. You now have enough pressure and enough temperature to overcome the Coulomb force and bring these protons close enough to each other for fusion to occur. For fusion, ignition. And the reason why is, and I want to be very careful, it's not ignition, it's not combustion in the traditional sense. It's not like you're burning a carbon molecule in the presence of oxygen. It's not combustion, it's ignition. And the reason why it's called ignition is because when two of these protons, or two of the nucleuses fuse, the resulting nucleus has a slightly smaller mass. And so in the first stage of this, you actually have two protons under enough pressure. Obviously, this would not happen with just the Coulomb forces. With enough pressure, they get close enough, and then the strong interaction actually keeps them together. One of these guys degrades into a neutron. And the resulting mass of the combined protons is lower than the mass of each of the original by a little bit. But that little bit of mass results in a lot of energy. Plus energy. And this energy is why we call it ignition. And so what this energy does is it provides a little bit of outward pressure so that this thing doesn't keep collapsing. So once you get pressure enough, the fusion occurs, and then that energy provides outward pressure to balance what is now a star. So now we are where we actually have the ignition at the center. And we still have all of the other molecules trying to get in, providing the pressure for this fusion ignition. Now, what is the hydrogen being fused into? Well, in the first step of the reaction, and I'm just kind of doing the most basic type of fusion that happens in stars, the hydrogen gets fused into deuterium. I have trouble spelling, which is another way of calling heavy hydrogen. This is still hydrogen because it has one proton and one neutron now. It is not helium yet. It does not have two protons. But then the deuterium keeps fusing, and then we eventually end up with helium. And we can even see that on the periodic table. Oh, I lost my periodic table. Well, I'll show you in the next video. But we know hydrogen in its atomic state has an atomic number of 1, and it also has a mass of 1. It only has one nucleon in its nucleus. But it's being fused. It goes to hydrogen 2, which is deuterium, which is one neutron, one proton in its nucleus, 2 nucleons. And then that eventually gets fused, and I'm not going into the detail of the reaction, into helium. And by definition, helium has 2 protons and 2 neutrons. So it has, or we're talking about helium-4 in particular, that isotope of helium. It has an atomic mass of 4. And this process releases a ton of energy because the atomic mass of the helium that gets produced is slightly lower than 4 times the atomic mass of each of the constituent hydrogens. So all of this energy from the fusion, but it needs super high pressure, super high temperatures to happen, keeps the star from collapsing. And once a star is in this stage, once it is using hydrogen, it is fusing hydrogen in its core where the pressure and the temperature is the most to form helium, it is now in its main sequence. This is now a main sequence star. Main sequence star. And that's actually where the sun is right now. Now, there's questions of, well, what if there just wasn't enough mass to get to this level over here? And there actually are things that never get to quite that threshold to fuse all the way into helium. There are a few things that don't quite make the threshold of stars that only fuse to this level, so they are generating some of their heat. Or there are even smaller objects that just get to the point there's a huge temperature and pressure, but fusion is not actually occurring inside of the core. And something like Jupiter would be an example. And you can go several masses above Jupiter where you get something like that. So you have to reach a certain threshold where the pressure and the temperature due to the heavy mass gets so large that you start this fusion. But the smaller you are above that threshold, the slower the fusion will occur. But if you're supermassive, the fusion will occur really, really fast. So that's a general idea of just how stars get formed and why they don't collapse on themselves and why they are these kind of little balls of fusion reactions existing in the universe. And the next few videos we'll talk about what happens once that hydrogen fuel in the core starts to run out.